We've all seen the headlines about AI writing code generating incredible images, but have you ever stopped to consider what these seemingly intelligent systems still struggle with?
Hmm.
I'm talking about something that comes so naturally to us, just looking at a picture and understanding it. The relationships between objects, the underlying patterns, the visual logic.
Yeah, absolutely.
It makes you wonder, doesn't it? If AI is this advanced, why does it sometimes seem completely stumped by visual tasks that, well, a child could solve?
That's the central question, really. And it brings us right to this crucial concept of visual reasoning. This
Right.
isn't just about, processing pixels. It's fundamental to intelligence, both human and artificial.
Right.
It involves interpreting visual information to solve problems, make inferences, draw conclusions. Think about reading a map. You're constantly using visual reasoning.
Exactly. And it turns out really testing this visual reasoning in AI, well, it's been more complicated than maybe we first thought. And that's where our deep dive today begins, with a new benchmark called VisuLogic. This tool is specifically designed to rigorously evaluate the visual reasoning capabilities of multimodal large language models, or MLLMs as we often call them.
Yep.
For this discussion, we're drawing directly from the research paper that introduced VisuLogic, so, we're getting the insights straight from the source.
And what makes VisuLogic particularly interesting, I think, is that it's been carefully built to avoid the limitations of many existing AI benchmarks.
Oh, so?
Well, you see, a lot of current evaluations, maybe unintentionally, allow models to use text descriptions that come with the images as a kind of shortcut.
Ah, okay.
So they essentially bypass the need to truly see and understand the visual content itself. VisuLogic tries to tackle this head-on by focusing on problems where the visual part is absolutely essential. You can't just read your way to the answer.
Gotcha. So our goal today is to really dig into this challenge. Why is visual reasoning proving such a hurdle for AI? What does VisuLogic reveal about these difficulties? And what potential solutions are researchers exploring to help AI genuinely see and understand the visual world more like we do?
Sounds like a plan.
Okay, let's unpack this. What were the problems with how we were testing these models? You mentioned shortcuts.
Right. The core issue, as the research paper points out, is that many current evaluations for MLLMs don't truly isolate visual reasoning.
Mm.
Often these tests include tasks where a model can cleverly use the text that comes with the image to get the answer without really engaging deeply with the visual information itself.
Can you give an example?
Sure. Think about referring expression comprehension tasks like VLMR1 as one mentioned. These usually involve finding a specific object in an image based on a text description.
Like find the blue car.
Exactly. And while that does test some connection between language and vision, it often just boils down to basic object localization pointing to the right thing. It's not really demonstrating a deep understanding of the whole scene.
Right. It's more about find the red apple than understand why this arrangement of fruit looks balanced or something like that.
Precisely. And this isn't just for simple tasks, even benchmarks that seem more complex,
Right.
like math problems with diagrams, things like Math Vista, MathVerse, MathVision, they can have this issue too.
But isn't the point there to understand the diagram?
Well, that's the intention. You want the AI to understand the graph or the geometric figure and use that to solve the math. But what researchers found is that many MLMs tend to just sort of translate the visuals into a text description first,
Oh.
and then they lean on their already pretty strong language reasoning skills to figure out the solution from the text.
So they're not really seeing the mathematical relationships in the diagram itself. They're just processing a textual summary of it and crunching the numbers based on that. It feels like they're finding a workaround, doesn't it?
It really does. And this leads to a fundamental problem. We might be, mistakenly giving models credit for visual reasoning when it's actually their language processing doing the heavy lifting.
So we get a misleading picture of how well they actually see.
Exactly. It really highlights how much our own understanding of space, for instance, is tied to direct visual experience, and how hard it is to fully capture that in words alone.
Okay, so if those older tests weren't truly getting at visual reasoning, what makes VisuLogic different? How did they build a benchmark focused purely on the visual side?
Well, VisuLogic was specifically designed to get around those limitations. It focuses on tasks that are inherently difficult, maybe even impossible, to solve using just text. The researchers put together a set of 1,000 problems, all checked by humans, across 6 distinct categories.
1,000 problems, okay.
And the key thing is, these problems demand a deep understanding of visual relationships, transformations, attributes, things that are just really hard to fully describe textually.
6 categories, you said. What
Yeah.
kinds of skills are they testing?
Yeah, the paper breaks it down in the data taxonomy section.
Hmm.
First up is quantitative reasoning. This looks at understanding changes in, like, the number of visual elements, counting points, lines, angles, and also grasping arithmetic relationships between shapes.
Okay. Counting and basic math with shapes.
Then there's spatial reasoning. Think about those puzzles where you have to mentally unfold a docs.
Oh, yeah. Those are tough.
Right. That's the kind of thing. It tests if the model can mentally reconstruct 3D shapes from 2D images, visualize folding or unfolding surfaces, integrate different 3D structures, like seeing a net and knowing if it makes a cube.
That definitely feels like something very visual, hard to just describe.
Exactly. Next is positional reasoning. This is about understanding transformations, like moving objects translation or rotating them, reflecting them, while their basic properties stay the same.
So tracking how things move or change orientation.
Uh-huh. Then there's attribute reasoning. This gets into the inherent characteristics of shapes. Things like symmetry, axial, or central curvature, whether a figure is open or closed.
So recognizing a circle is symmetrical or a triangle is a closed shape, basic properties.
Precisely. The fifth is stylistic reasoning. This is about changes in how objects look visually, like if one shape is overlaid on another, or part of a shape is missing, or just judging how similar or different the style of two shapes is.
That sounds subtle.
It can be. And finally, there's an other category. This catches questions involving things like letters, alphanumeric symbols, or other special characters within the visual problem.
Wow, that covers a really wide range of visual skills. Does the paper say how the questions are split between these categories?
Yes. Figure 1 in the paper shows the distribution. Quantitative reasoning is the biggest chunk, about 35%. Spatial reasoning is next at around 23%. Then positional reasoning at roughly 14%. The rest, other, style, and attribute, are smaller, like 8 to 10% each.
Okay, so a strong focus on quantitative and spatial aspects.
Seems so. It gives you a sense of what the researchers prioritized.
Now, you mentioned earlier how models might translate visuals to text. The paper had an interesting comparison related to that, right? With another benchmark, MMMU.
Yes, that was quite revealing. Figure 2 compares how this MLLM description LLM pipeline works for MMMU versus VisuLogic.
What's the pipeline again?
It's where you have the multimodal model, the MLLM, look at the image and generate a text description, and then you feed only that text description to a separate powerful language model, LLM, to see if it can answer the question.
Got it. So how did it work for MMMU?
For MMMU, which tests advanced reasoning in fields like chemistry or physics using diagrams, they found that good MLLMs are pretty good at describing the key visual details in text. And that text description is often enough for the language model to then figure out the correct answer. It shows again how language reasoning can often solve these visually grounded problems in MMMU.
But it was different for VisuLogic.
Completely different. When they tried the same approach with VisuLogic questions, even the best MLLMs really struggled to describe the images accurately enough.
Why? What was missing?
Crucial visual cues. Things like the specific type of symmetry or the exact degree of rotation or subtle stylistic changes, these details often got lost in translation to text.
And those details are critical for VisuLogic problems.
Absolutely. So the language model getting the description was missing vital information and, well, often got the answer wrong.
So the very act of trying to put the VisuLogic images into words caused information loss. That really drives home the point about needing genuine visual understanding.
That's exactly it. Textual reasoning alone just isn't sufficient for VisuLogic. It really underscores why this benchmark is a strong test of visual, not just language, abilities.
Okay, so VisuLogic is designed to be tough visually. How did the big MLLMs actually do when they took the test? What were the scores like?
The results? Well, they're quite sobering, actually. They're in Figure 1 and Table 1. Leading models like GPT-4o, Dubao 1.5 Vision Pro, Gemini 2.0 Pro, Intern VL378B, their overall accuracy was only around 26 to 28%.
26 to 28%. That sounds low.
It is, especially when you consider that just randomly guessing one of the 4 multiple-choice answers gives you a 25% chance.
Wow, so they're barely better than random guessing.
Pretty much. Only slightly better. It really highlights the difficulty.
And how does that compare to humans?
Humans did much better, though still found it challenging. The paper reports an average human accuracy of 51.4%.
Okay, so 51% versus like 28%. That's a huge gap, over 20 points.
It is. It really shows how far these models still have to go in terms of robust visual reasoning.
And what about using just text models? You said that MLLMs struggled to describe the image as well, but if you gave a good description to a text-only model, did that help?
Interestingly, no, not really. The accuracy of powerful text-only LLMs, like Dubeo 1.5 Pro, Cloud 3.7 Sonnet, Quantitative 2.572B, even when given detailed image descriptions, was also stuck in that same range, around 26 to 28%.
Huh. So even with a good description, the reasoning part is still the bottleneck.
It strongly suggests that yes, you really seem to need to see and process the visual information directly for these kinds of logic problems. Text alone doesn't cut it.
The paper also looked at chain of thought prompting, right? That technique where you ask the model to think step by step. That usually helps reasoning. Did it work here?
Surprisingly, not much. Table 2 shows that Coney 2 prompting gave only tiny improvements, usually less than 1 percentage point.
Why would that be?
The researchers think it might be because current Cody training is mostly focused on text-based reasoning problems. It might not translate well or hasn't been trained effectively for the kind of visual logic VisuLogic requires.
That's fascinating. So step-by-step thinking isn't automatically helpful if the steps involve visual intuition. What about giving hints? Did that help more?
Hints did make a more noticeable difference, yeah. Table 3 shows this. When models got hints based on the actual solutions, some of them like Claude 3.7 Sonnet, Gemini 2.0 Pro, saw their scores jump by about 8 percentage points.
Okay, so hints help get them into the mid-30s accuracy range.
Right, but even with hints, they were still way below human performance. Humans with hints jumped to over 83% accuracy.
Wow. Okay, so hints guide them, but don't fix the underlying reasoning issue.
Exactly. It suggests improving the core reliability of their visual reasoning is the crucial part.
Now, what about model size? Does bigger mean better for VisuLogic? We usually hear that larger models are more capable.
Yes, Table 1 does show a positive trend. There's a correlation between the number of parameters and performance.
For instance.
Well, like in the Quinn 2.5 EL series, the bigger 72 billion parameter model did a bit better than the 7 billion one. Same for Intern VL 2.5, the 78 billion parameter version beat the 38 billion one.
But it wasn't a magic bullet.
No, definitely not. Even the largest models were still struggling significantly, only hitting that high 20s accuracy range. So just making models bigger isn't the whole answer for visual reasoning, it seems.
And open source versus closed source models, did one group do clearly better?
Actually, no. The performance was remarkably similar. The top open source model mentioned, Intern VL3 at 70B, scored 27.7%. The top closed source one, Dubao 1.5 Vision Pro, got 28.1%.
Very close.
Yeah, and others like GPT-4o and Claude 3.7 Sonnet were in the same ballpark. It suggests this visual reasoning challenge isn't specific to one type of model or training method.
So it's a broader issue across the field.
It kind of hints that maybe visual reasoning just hasn't been a primary focus in how most current MLLMs are trained, whether they're open or closed source.
Okay, so it's clear these models find VisuLogic really challenging across the board. Did the error analysis show where they struggle the most? Which categories were hardest?
Yes. Figure 8 in the paper gives us some really good insights there. For the text-only LLMs, Figure 8a, the biggest problem area was spatial reasoning.
That makes sense given what we said about describing 3D stuff in text.
Exactly. It's just very hard to convey that complexity textually. They did relatively better on quantitative reasoning, suggesting numbers are maybe easier to handle via text.
Okay. And what about the multimodal models, the MLLMs that can actually see the image? Where did they trip up most? Figure 8b.
Their biggest struggle, surprisingly perhaps, was with stylistic reasoning. Their error rates here were over 75%.
Over 75%. That's worse than random guessing.
It is. It really points to a fundamental weakness in picking up on subtle visual cues, like overlays, contours, how shapes look stylistically.
You'd think the models processing images directly would be better at style. How did humans compare on errors? Figure 8c.
Human errors showed a different pattern. Humans were particularly strong on positional reasoning, keeping errors below 30%. They seem pretty good at tracking how things move and relate spatially.
But the models struggled more there.
Yes. Both the text-only and multimodal models had more trouble with positional reasoning than humans did. It highlights a key difference in how we process spatial relationships compared to current AI.
So the very tasks humans find relatively easy understanding movement and position are harder for the AI. Did the paper give concrete examples of these failures?
It did. In the qualitative analysis section,
Yeah.
Figure 6 has some good ones. Figure 6 shows a text-only LLM getting things wrong because the image caption it relied on missed key details, like the pattern of black and white dots changing.
So the text description just wasn't good enough.
Right. And Figure 6 also shows MLLM failures. Sometimes the models could correctly list the static objects in an image,
Uh-huh.
but then completely miss the relationship or the pattern of how those objects were changing or interacting. Like they might just count things instead of seeing the rule behind the changes.
So they see the pieces, but not the dynamic logic connecting them.
Exactly. It shows a limitation in reasoning about visual dynamics, not just static scenes.
It seems like a major gap. Now, the researchers didn't just point out problems, they also explored a way to improve things using reinforcement learning, right?
Yes, that's one of the more promising directions highlighted in the paper. RL.
How did they use it?
They took some baseline models and fine-tuned them using reinforcement learning on an extra data set of similar visual reasoning problems.
And did it work? What were the results?
The results were encouraging, yeah. They're in Table 1.
Yeah.
For example, using RL boosted the Quen 2.5 VL7B model from about 25.5% accuracy up to 28.0%, and Intern VL 2.538B saw an even bigger jump from 25.5% up to 31.1%.
Okay, 31% is starting to look a bit better, moving away from random chance.
It is. And notably, these RL-tuned models actually outperformed some of the larger models that hadn't had RL fine-tuning.
So RL seems to be doing something useful. What is it about RL that helps with these visual reasoning challenges?
The researchers think RL encourages a deeper, more step-by-step kind of logical reasoning process.
So
Figure 6G gives an example with chess pieces. The RL-enhanced model was better at tracking how the pieces move the state transitions and predicting the next board layout. It seems RL helps the model learn to sort of iterate, revise its ideas, almost like trial and error, to reach a better conclusion.
So it's learning a better thinking process.
Seems like it. They used a specific rule-based RL approach that rewarded the model for outputting its reasoning in a clear format and, of course, for getting the right answer. It guides the model towards more structured reasoning with visuals.
So it's not just about seeing more examples, but actively training a better way to think about the visual problem.
Precisely. It seems to nudge them towards a more deliberate process when faced with visual logic.
This has been a really fascinating look at, well, what AI can't quite do yet with vision, and how benchmarks like VisuLogic are trying to push things forward. To wrap things up, what are the main takeaways here?
I think the biggest one is that VisuLogic really shines a light on a significant gap. There's a big difference in visual reasoning between humans and even our best MLLMs today.
Right. The models often take textual shortcuts when they pan.
Exactly. And they really struggle when forced to rely purely on visual understanding and logical deduction. They can process images incredibly well. But that deep, nuanced understanding humans have, that's still a major hurdle.
And benchmarks like VisuLogic, which are designed to be vision-centric, seem crucial for making progress.
Absolutely. By minimizing the language shortcuts and really testing the visual reasoning itself, VisuLogic helps researchers get a truer picture of model capabilities and where the weaknesses lie. It gives clear targets for improvement.
And that work using reinforcement learning seems like one promising path forward.
It definitely looks promising. Those early results suggest RL fine-tuning could help build more stepwise, iterative reasoning skills in these models.
Yeah.
But, the paper also makes it clear there's still a long way to go to reach human-level visual reasoning.
It certainly leaves us with something profound to think about.
Mm.
If we want AI to truly understand and interact with our world, mastering visual reasoning isn't just some optional extra. It seems absolutely fundamental.
Mm.
It makes you wonder what other seemingly simple human cognitive abilities are proving surprisingly tough for AI, and what does that tell us about intelligence itself? Maybe you, the listener, might want to check out the VisuLogic paper for even more detail. Thanks for joining us for this deep dive.